Hey everyone, today we're going to talk a little bit about the introduction to Chapter 5, the basic rules of probability. So the first thing we're going to talk about is a probability model. We're going to talk specifically about how probability has to do with the chance of something happening, specifically the chance of an event happening. And we're talking about short run behavior versus long run behavior. So let's say I'm flipping a coin and I'm flipping the coin 10 times and I want to know how many heads out of 10 I get. Let's say I flip a coin 10 times and I end up getting 6 heads out of 10 or even 8 heads out of 10. In the short run, it is more likely that I could get something rare like 8 heads out of 10. And that can be graphed as pointing here to this graph here, the number of tosses on the x-axis. Let's say I tossed the coin 10 times and I ended up getting 8 heads, okay? So it's kind of jagged here, and this jaggedness is showing that it is kind of unpredictable in the short run, the number of heads I could get. So maybe I just do 8 out of 10, and I get 0.8, the probability of getting heads, okay? But in the long run, if I increase the number of tosses to 500, it's going to be more and more that the proportion of heads that I get will be closer to 50%. So in the short run, if I only have a sample of size 10, I might only have, I can have 8 out of 10 heads. But in the long run, as I do 500 tosses, the number out of 500 should be close to 250. And that is called the law of large numbers, okay? So the law of large numbers says, as the sample size, which is in this case the number of tosses, increases, and the number of trials in this case increases, the probability, which is the experimental probability, will get closer and closer to the ideal probability. Sorry, I'm spelling it wrong. So I'm going to read what this says because I know it's a little unintelligible here. As the sample size increases and the number of trials increases, the actual probability, which is called the experimental probability, will get closer and closer to the ideal probability, which is like the theoretical probability. So in the case of the coin flip, the more times I flip the coin, the more and more that the proportion of heads when I record it will become closer and closer to that 0.5 in this case. Okay, that's the law of large numbers. So that's why we really want to do a large sample size, because if you have a small sample size, it could be like an outlier or a fluke happening, but in the long run, it should be more and more ideal. So now let's talk about a sample space. A sample space is just a list of all the possible outcomes for an event. So if you look down below, it says, what is the sample space when a coin is flipped? So when I flip a coin, the outcomes that I could possibly get are just heads and tails, okay? That's the list. I could get heads or I could get tails for a single coin. And for a die, I could just get 1 through 6. 1, 2, 3, 4, 5, or 6 when I roll a single die, right? So I write the sample space the same way that I would write a solution set in algebra. I put these squiggly brackets here, and that's what I do. So the sample space is the list of all the possible outcomes. Now, obviously, these are kind of simple events. We call an event basically just something that we're doing with probability. So the coin flip is an event, the die roll is an event. And now here we have a coin is flipped and a die is rolled. So I could actually list out all these probabilities by kind of pairing them together here. I can list H1, H2, H3, H4, H5, H6. And what does that mean? That means I got heads on the coin and 1 on the die. I got heads on the coin and 2 on the die, etc. And then I could also get tail 1, tail 2, tail 3, tail 4, tail 5, tail 6, okay? So that is the full sample space here. So basically, that concept is listing out all the possible outcomes is the sample space. Now, what I could have done instead of what I just did, which is list them all out, is a handy way to get your sample space is create what's called a tree diagram. So a tree diagram would be, you would represent the first event, which in this case was the coin flip, heads, tails, like so, showing either heads or tails for the first branch, representing the first outcome. And then the second branch is going to represent the second event, which is the die roll. So we could get 1, 2, 3, 4, 5, or 6 for the die roll, no matter what I got on the coin flip. So I'm going to list it twice because I could either get heads or heads and 1, 2, 3, 4, 5, 6 on the die, or I could get tails and 1, 2, 3, 4, 5, 6. So the first column here, if you're looking vertically, is the coin, and then the second column is the die. Okay. So like when I'm saying vertically, this first column here is the coin, and then the second column here is the die. All right. So now if you total it all up and you count the total number of branches, you're going to get the total number of outcomes in the sample space. So if I list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there's actually 12 total outcomes in my sample space. So if I looked back here, if I had counted all these, indeed, there are 12 total outcomes, okay? And now it turns out what I could have done in order to compute it is do what we call the multiplication principle. So I could have done the number of outcomes on the coin, which was 2, heads or tails. And then I could have done the number of outcomes on the die, which is 6, 1, 2, 3, 4, 5, and 6. And then you can multiply them together because and means multiply in probability. I'm doing a coin and a die. So 2 times 6 equals 12. So there are 12 total outcomes in my sample space for the combination of events of the coin flipped and the die rolled. So what I'm about to do is create what's called a probability model. A probability model is going to be a list of all the outcomes, which is actually has 2 parts. It's the sample space, which is the list of all the outcomes that we have here. And then the second part is going to be the respective probabilities of each of these outcomes, okay? So what do I mean by that? If I'm talking about the coin flip, I can write it as a little table. The outcomes are heads and tails, and then the probabilities, P of X, is going to be 1/2 and 1/2. Similarly, I could list the die roll, and that would be the outcomes 1, 2, 3, 4, 5, and 6. And then I can list their respective probabilities, 1 out of 6, 1 out of 6, 1 out of 6, etc. And these are going to actually total up to 6 out of 6, which is 1 whole. These are all called equally likely because it's equally likely that I could get a 1 out of 6 or 2 out of 6 or 3 out of 6, etc. Now, the reason why the tree diagram is helpful is because if you have more than one event, sometimes the tree diagram is a nice way for us to organize ourselves. So let's say I'm flipping 3 coins. This is really 3 events here, a coin flip and a coin flip and a coin flip, okay? First, it says interpret the probability of getting 3 heads if the probability is 1 out of 8. So interpreting the probability just has to do with in the long run what's happening. So we want to say if we flip 3 coins many times, 1 out of 8 of those times, we will get 3 heads. That's basically what we're doing here. So if we flip 3 coins many times, like infinite times, 1/8 of the time, we will get all 3 heads. Okay. You could actually make that a percent as well if you prefer. If we flip 3 coins many times, 1/8 of the time we will get all 3 of them heads. So can I guarantee that I'm going to get all 3 heads if I flip a coin 3 times? I'm hoping you're going to say no, it's not guaranteed, because this is a one trial scenario. In the short run, I might not get 3 heads, right? It's just in the long run, I should get 1 out of 8 times 3 heads. So in the short run, this is not guaranteed. It's more of in the long run, it is more likely, meaning infinite times 1 out of 8 will be 3 heads. Okay, so it's not guaranteed. Probably is not guaranteed unless you do something infinite times. So the next question says, Mr. Kim flips a fair coin 4 times and each flip lands heads up. He says there's no way he'll flip heads again. Next one's definitely going to be tails. Explain what is wrong with this reason. So I'm hoping that you are kind of understanding the concept of that coins are actually independent of each other. And it doesn't really matter if you get, in this case, 4 heads in a row. You could possibly get another tail in the short run, but in the long run, if he did this more than 4 times or 5 times, if he did it infinite times, then he should not be getting 3 heads in a row all the time. Okay, so now we have 2 fair dice. So these are the outcomes of all the possible outcomes if we had rolled 2 dice. So do you guys see that there are a whole bunch of outcomes, and we could count them out, but we can also use the multiplication principle to predict the number of outcomes. So how many outcomes on the first dice? I'm hoping you're going to say 6. And on the second dice, also 6. So if you do 6 times 6, you're going to get 36. And that is the total number of outcomes in this entire sample space here. So you could get a 1 and a 1, 1 and 2, 1 and 3, etc., all the way to a 6 and a 6. So since the dice are fair, each outcome has a 1 out of 36 probability, and they are all called equally likely. Okay? So let's say we wanted to get a sum of a 5. How many outcomes could we get a sum of a 5? So look here, and can you think about how many you can get a sum of a 5? Think about it and write it down. So I'm hoping that you saw that there were 4 ways that you could get a sum of a 5. 4 and 1, 3 and 2, 2 and 3, and 1 and 4. So there's actually 4 ways out of how many total ways? 36, right? So when we were doing probability, you see the word P, that means probability. You have to take it out of the total, okay? So we said there's 36 total outcomes in the sample space. So in this case, the desired outcome is the sum of a 5. Number of possibilities is 4 out of total 36. So you could either write 4 out of 36 or you could reduce it. So now you guys do sum of a 6 and write it down. I'm hoping that you saw that there are 5 ways to get a sum of a 6. There are 3 and 3, 4 and 2, 2 and 4, 5 and 1, and 1 and 5. So 1, 2, 3, 4, 5 going down the diagonal here. So that is going to be 5 out of 36. So now, if you look ahead, it says, what is the probability of rolling a sum of a 5 or a 6? Okay, so here's one of the rules that we need to talk about. It's the word or. So what do you think? So first thing is I'm going to show you guys some notation. 5 or a 6 can be notated with this thing. This is called a union. Union means or. And I'm hoping that you're going to think that the probability of getting a 5 was 4 out of 36, which was down this diagonal. And the probability of getting a 6 was 5 out of 36. So all we have to do is add 4 over 36 plus 5 over 36. It's going to be the probability of a 5 plus the probability of 6. So 4 over 36 plus 5 over 36 equals 9 over 36. And that is called union. So if you ever see the word or means add. or means add, okay? But it's very important to note that those events are called mutually exclusive. And what does mutually exclusive mean? It actually means that these events have no overlap. They have no intersection. And that means that we can just straight add them. Okay, so they have no shared outcome. No shared outcome. Another name for mutually exclusive is the word disjoint. Okay, so what do I mean by this? Well, if you look down below, there is a Venn diagram here. This is event A and event B. Event A would be rolling a 4. Event B would be rolling a 5. So there, if you roll a 4, you can't roll a 5. If you roll a 5, you can't roll a 4. You either roll a 4 or you roll a 5. You can't roll both at the same time, basically. They can't both happen at the same time. So maybe we should add that. Can't happen at same time, simultaneously, right? Means at the same time, okay? So if they can't happen at the same time, then the addition rule is you're allowed to just add them together. So you are allowed to add the probability of A to the probability of B. The probability of A or B is equal to the probability of A plus the probability of B, and you're done. So in the case of 4 and 5, rolling a 4 and rolling a 5, or rolling a 5 and rolling a 6, like I said above, sorry, if you can't roll a 5, if you roll a 5, you didn't roll a 6. If you roll a 6, you didn't roll a 5. So you're allowed to just straight add them together, and you're done. Yay. Okay. However, so sorry, let me change this to 5 and 6. My bad. Now, what if, however, we had something like rolling a 6 is A and rolling an even number? Okay. Now it gets a little crazy because it turns out that there is an option or an overlap or a shared outcome of a 6 and an even number. And that is called the intersection. So if there is an overlap or an intersection, it gets a little more complicated because then you can't just add, because if you do, you're going to be counting some things twice, okay? So what do I mean by that? Going back to my picture, I'm just going to erase the 5s. I'm just going to stick with the 6s, right? Okay. So I don't know if you guys can see this, but I highlighted all the even numbers, even numbered sums, and they're all yellow, and it's all every other. And it turns out there's half of these 36, which is 18 even numbered sums, okay? Because of half, right? But then if you look down the diagonal at what I circled, those were all getting a 6. There's 1, 2, 3, 4, 5 ways to get a 6, right? So there are sums that are even that are also a sum of a 6, that you can both be even and be a sum of a 6. So if you look at my Venn diagram here, these events overlap. It is possible to both be even in the middle and also be an even sum. So in the case of the 6s, all the 6s are even, right? So there were 5 ways, yep, to get a 6. There's 5 of them here. And then the evens, there's 18, right? But we can't just add the 18 plus 5 together, because if we added 18 plus 5, we would be counting these twice because they're already accounted for in the 18. So we have to do something different. We have to do 18 plus 5 minus the overlap, which is 5. And you end up getting 18 out of 36. Before we move on, I do want to do one more example with that. And that one, I'm just going to do a fresh start. This would be for the people who understand cards. So if you are doing cards, there are actually let's say we're going to do queens, and red, okay? Can you be a queen and be red? And the answer is yes. There are actually 4 queens in the deck. And for those of you that know cards, the 4 queens are, 2 of them are black and 2 of them are red. They are spades, clubs, diamonds, and hearts. Okay, so there's 4 total queens in the deck. The 4 of hearts, the queen of hearts, the queen of diamonds, the queen of spades, the queen of clubs. Okay, now there's actually half the deck, 26 cards are red. Okay, but there is an overlap between queens and red because there are 2 queens that are red. So if I wanted to find the probability of queen or red, if I added the probability queen to the probability of red, I would actually be wrong because if I do 4 out of 52 plus 26 out of 52, and I get 30 out of 52, I'm actually counting 2 of the queens twice. The 2 that are in the intersection, I'm counting them twice. So we can't just add because the events are not mutually exclusive. Since they share an outcome, what we're going to have to do you know, is subtract the 2 that are in the overlap. And you end up getting 28 out of 52. So the last thing I want to do is sum up this slide here. These are all the basic probability rules. The first one says the probability of any event is between 0 and 1. Okay, that means that the highest the probability could be is 1 or 100%. That is called certainty, aka 100% possibility. And 0 is called impossible. Okay, so probability is usually a number in between 0 and 1. The probability of the whole sample space equals 1 or 100%. That would be if you added all the probabilities up, they should equal 100%. So for example, the probability of heads and tails is 1/2 plus 1/2 or 2 out of 2, which is 100%. Probability of 1 through 6 on a dice is 1 out of 6, 1 out of 6, 1 out of 6. That got to add up to 100%. To get the probability, you do a fraction where you take your desired number of outcomes and you divide by the total in the denominator. Another thing I didn't talk about is complements, okay? I'm going to use the letter E for complement, all right? So let's say I say the probability of rolling a die and rolling a 5, a single die. You should tell me it's 1 out of 6, right? What's the probability of not rolling a 5? Well, the complement of rolling a 5 is not rolling a 5. So it's actually denoted with this little C here. It means the complement of rolling a 5 complement. So it's just going to be 1 minus 1/6, or 6 out of 6 minus 1 out of 6. And that's 5 out of 6 because the complements have to add up to 6 out of 6. So the probability of rolling a 5 is 1 out of 6. Probability of not rolling 5 is 5 out of 6. And lastly, the addition rule, if the events are mutually exclusive, meaning no overlap, we are allowed to just straight add them. So going back to that picture, I want you to visualize the picture of the 2 circles that don't intersect. Those are mutually exclusive, and you're just allowed to add, okay? So one last example of that would be if you're doing cards, and you were doing, let's say, queens and kings. If you're a queen, you're not a king. If you're a king, you're not a queen. So you're either a king or a queen. There are 4 kings in the deck. There are 4 queens in the deck. Thus, the probability of getting a queen or a king is equal to the probability of queen plus probability of king. You're allowed to just add 4 out of 52 plus 4 out of 52 equals 8 out of 52. And you're done. So these events are called mutually exclusive if they do not overlap.